All right, Hess students, this is Mr. McMahon. We're going to walk through this lesson. Today is going to be probably day 2 of our energy flow through an ecosystem unit. And we're going to walk through today kind of the concepts and how to do some of the calculations in this unit. So you should have a calculator out. So we are looking at how energy flows through an ecosystem. By the end of today's lesson, we should be able to answer these 3 questions. What happens to energy that enters an ecosystem? How does energy enter and leave an ecosystem? And then finally, matter cycles through an ecosystem, but how does energy move through an ecosystem? So we'll start with part 1. So how energy enters an ecosystem. It's answering our first essential question. Light energy, also known as electromagnetic energy, along with air and water, is converted into chemical energy, glucose, also known as C6H12O6, through the process of photosynthesis. The model below provides evidence that shows how energy enters an ecosystem. If we look at this model, we see we have 100,000 calories of electromagnetic energy, in this case light energy. We have a plant. That tree converts that light energy into chemical energy, namely glucose, 100,000 calories of glucose. So what was 100,000 calories of light energy is now 100,000 calories of glucose or chemical energy. You'll notice in the model that some of the glucose molecules have been colored red and some of the glucose molecules have been shaded in green. That's to show what the plant does with all of that glucose that it's made. Most of the glucose you can see out of the 100,000 calories, 90,000 of calories of glucose is going to be converted into thermal energy or heat energy, leaving only about 10,000 calories to build the plant's biomass. So only about 10,000 calories of glucose will be left over to build leaves, branches, bark, roots, stems, basically plant biomass. And throughout this model, we show that no calories were created, no calories were destroyed. In other words, we have to keep track of every calorie of energy. So the number 1, energy enters as electromagnetic energy, also known as light. Energy is converted into chemical energy, namely glucose. That's what becomes plant biomass. How does the model show that no energy was created or destroyed? Well, as I said, 100,000 calories of light is converted into 100,000 calories of glucose. Not a single calorie was created or destroyed. So let's go ahead and kind of look at how these calories are broken down. In order for the tree to stay alive, it must perform jobs that sustain its life. So below is a list of jobs that the tree must perform in order to remain alive. Use the data below on the model on the previous and the model on the previous page to explain what most of the chemical energy glucose is transformed into. So we see here we have on the left-hand column plant jobs of life. And these are just some of the jobs that the plant or the tree is going to perform. It's got to copy its DNA. It needs 3,000 calories to do that. It's got to fight off infection. It needs 10,000 calories to do that. It's got to move a molecule from its root to its leaf. It requires 25,000 calories to do that. It's got to make an aroma molecule. It's got to make a poison. It's got to resist the pull of gravity. All of that combined, all of those jobs of life, take 90,000 calories of energy to power. So if we go back to our model, that's the 90,000 calories of red glucose that's converted into heat to power those jobs of life. So what process performs this conversion of glucose, of chemical energy into thermal energy? The process of cellular respiration. That's what releases energy from glucose to power the jobs of life. So the tree does not burn all 100,000 calories of glucose. The tree stores the 10,000 calories of glucose that it did not burn as biomass. So that's the remaining 10,000 calories becomes leaf, root, stem, bark, basically the stuff that builds the plant. The stored glucose is available as food for the next trophic level. So the glucose that was not burned is now stored as biomass in the plant, and that's what's available as food to the herbivore. So we need to intro some other terms here. The term gross primary productivity, also known as GPP. This is the total amount of light energy converted into chemical energy by plants. So for example, if you had 100,000 kilojoules of light energy converted into 100,000 kilojoules of chemical energy, also known as glucose, through photosynthesis. So it's the total amount of light energy converted into glucose. So GPP is a term that only applies to plants because only plants perform photosynthesis. NPP, also known as net primary productivity. This is the biomass built by a producer. In other words, the stems, the roots, the leaves, the branches. This is the biomass built up by the producer that is available to the next trophic level to eat. All plants use some glucose energy to fuel their own jobs of life. NPP is the plant biomass that is left over after the jobs of life. So NPP is the energy available for herbivores to eat. NPP is producer biomass that is available to the next trophic level, all right? So there's a little formula here that we've got to know. Producer biomass, that's your NPP, equals the GPP, that's the total amount of glucose made, minus the energy for jobs of life. So let's apply that formula to our little model. Use the example from the first page, list the values below. So in our case, GPP was 100,000 calories, NPP was 10,000 calories, and the jobs of life was 90,000 calories. And we can see that here. You can see the 90,000 calories in red. You can see the 10,000 calories in green, that's your NPP. And then your total amount, your 100,000 calories, is your GPP. We're going to scroll back to that part. Okay, so we have seen three forms of energy in this simulation: light energy, thermal energy, and chemical energy. Which of these forms of energy is available to be eaten by the herbivores, and which energy is not available to be eaten by the herbivores? Well, we'll start with the 100,000 calories of light. No herbivore can eat light. We got the 90,000 calories of thermal energy. That's the glucose that was converted into heat to power the jobs of life of the tree. Well, herbivores can't eat heat, so that's not available. All that's left is the 10,000 calories of glucose that was not burned by the plant. That's what becomes plant biomass. That's what's available for the herbivore. So let's move on to part two. Again, keep in mind we have to account for every single calorie because we can't violate the law of conservation of energy. So let's do a quick recap. Energy enters an ecosystem when light is converted into glucose. That's your GPP. Plants will burn most of this glucose through cellular respiration to power the jobs of life that keep it alive, thus transforming most of the glucose into thermal energy. That leaves only a portion of the original 100,000 calories, 10 to be exact, 10,000 calories, for the plant to use as biomass. The biomass is the NPP that's available to the herbivores. So in part two, we're going to play the role of a herbivore. In this example, we are a giraffe eating a small portion of the tree. Trace what happens to the 10,000 calories of stored tree biomass energy as it's transformed into different forms of energy. The giraffe eats several leaves that collectively total 500 calories. The remaining 9,500 calories of tree go uneaten. The uneaten portion includes the bark, the branches, the roots, and even some of the leaves. This energy is impossible for the herbivore to eat as bark is too tough to chew and roots are underground. So a lot of this energy is uneaten and doesn't go to the next trophic level. This uneaten energy will be consumed by decomposers. So what happens then to the 500 calories of chemical energy, in this case leaves, that was eaten by the giraffe? What will it turn into? Well, it'll turn into three things. Some of the leaves will turn into waste. That's chemical energy. Some of the leaves will turn into giraffe, also chemical energy. And then some of it will turn into thermal/heat energy. So of the 500 calories of leaves, none of it's destroyed. All of it turns into a different form of energy. So let's introduce this concept of consumption efficiency. The consumption efficiency is the percentage of energy eaten by the consumer. In the case of the giraffe, it is the percentage of tree eaten by giraffe. Calculate the consumption efficiency. Well, in this case, we can see the formula for consumption efficiency is calories of food eaten all over total calories of that organism times 100. So in this case, the giraffe ate 500 calories of the 10,000 calories of tree. Multiply that times 100, and the giraffe only ate about 5% of the tree. So pretty low consumption efficiency. Let's kind of explore what happens to the 500 calories. The 500 calories of leaves are in the giraffe's stomach. Some of the leaf energy is too tough to digest, and that is converted into waste. The undigested 500 calories that becomes waste is what we call unassimilated energy. The portion of leaves that does not become waste is called assimilated energy. The assimilation efficiency for the giraffe is 60%, meaning 40% of the 500 calories becomes waste. So let's do some calculations. Calculate how many calories become poop. 500 calories eaten by the giraffe, and again, 40% of it is too tough to digest, the unassimilated portion. That means 200 of the 500 calories becomes waste. Much like the plant, the giraffe also has jobs of life that it must perform in order to remain alive. Each job requires energy to power. Therefore, cellular respiration will convert much of the 500 calories into thermal heat or heat energy. So let's kind of look at some of the jobs of life for the giraffe: fighting off infection, resisting the pull of gravity, foraging for plants, running from predators, pumping heart, copying its DNA. All of that requires energy. So some of the leaves will be used to power those jobs of life and convert it into heat. So in other words, we've got a formula here. The assimilated energy equals the energy for the jobs of life, that's the heat, plus the energy stored as biomass. That is a formula you will need to know. The remaining energy that is not used to power the jobs of life becomes giraffe biomass. This is called the production efficiency. I want you guys to remember production efficiency means consumer biomass. So when you see production efficiency, you should think biomass. That's the food that becomes part of the organism that ate it. So it's the part of the giraffe that becomes the lion. It's the part of the leaf that becomes the giraffe. That's production efficiency. Let's do some calculations. Calculate the assimilated energy if the giraffe's assimilation efficiency is 60%. Let's use our formula. Our assimilation efficiency is 0.6. The amount of energy eaten is 500. So that means 300 calories of the leaf become a combination of heat and giraffe biomass. Next question, calculate the amount of leaf that becomes giraffe if the giraffe's production efficiency is 40%. Remember, production efficiency is biomass. So I'm going to take the assimilated amount, in this case 300, multiply that times the giraffe's production efficiency, which is 40%, and that means of the 300 calories of assimilated energy, 120 becomes giraffe. We could also say that of the 500 calories eaten, 120 calories becomes giraffe biomass. We also need to calculate the amount of assimilated energy that becomes heat. Again, I take my assimilated amount, in this case 300, and I multiply it times 0.6. Because remember, if 40% becomes giraffe, that must mean the remaining 60% becomes heat. So 300 times 0.6 means 180 calories of the assimilated leaf energy becomes heat energy. That's the energy that powers the giraffe's jobs of life. So we went ahead and created a model of what this looks like. You had 500 calories of leaf. Of that, 100 became heat to power the giraffe's job of life. 120 calories of the 500 calories of leaf became actual giraffe. And then we can see some waste. 200 of the 500 calories became waste. All right, so no calorie was created or destroyed. Along comes a lion who's going to eat this giraffe. The lion's consumption efficiency is 85%, meaning it eats 85% of the 120 calories. The lion's assimilation efficiency is 55%. Remember, assimilation efficiency is both heat and lion biomass. And the lion's production efficiency is 8%. Remember, production efficiency is what becomes the lion's biomass. Let's do some calculations. Amount of calories of giraffe eaten by a lion. Well, The giraffe had 120 calories total. Lion ate 85% of it, so the lion ate 102 calories of the 120 calories of giraffe. The amount of calories of giraffe that becomes lion poop, remember, the assimilation efficiency is 55%. That must mean then that of the 102 calories eaten by the lion, 45% is the unassimilated amount. So in other words, 45.9 calories of what was eaten becomes poop. And then the last two calculations, the amount of calories of giraffe that was burned by the lion and converted into heat energy. Well, I've got to figure out the assimilated amount first. So I took the amount eaten, 102 calories, multiplied that times the assimilation efficiency, in this case 55%, and it turns out 56.1 calories of the 102 calories eaten becomes heat and lion biomass combined. How much of the 56.1 is heat or lion, we don't know yet. Then let's see if we can now figure out how much becomes heat. So I'll take the assimilated amount, 56.1, multiply that times 0.92, because remember, the lion's production efficiency is 8%, which must mean that 92% becomes heat, leaving 51.6 calories to become heat. Finally, I'm going to calculate the lion's biomass. Again, I take the assimilated amount, 56.1, multiply that times 0.8, because remember, the lion's production efficiency is 8%, so that tells us how much of the giraffe becomes lion. So I multiply 56.1 times 0.8, and it turns out 4.488 calories of giraffe became lion biomass. And so this is a set of calculations that shows how energy flows through an ecosystem.